Hello cadets, my name is Captain Boone Gilbreth from the Nuclear Engineering Program in the Department of Physics and Nuclear Engineering. I'm here today to talk to you about radioactive decay and radiation dose. And the first thing we want to do in introducing this topic is to give you a snapshot of some notation that you'll see throughout this block of instruction and if you go into the nuclear engineering track or the nuclear engineering major. So the notation we show you here is simply a way to abbreviate a radioactive nuclide, or in fact any nuclide that you need to write as part of an equation or in notation in a report. And the first thing we want to start with is the chemical symbol denoted here by X, and that is pulled straight from the periodic table of elements, C for carbon, U for uranium, things like that. And the next thing we have in the upper left is a superscript. That's the mass number given by A. This is also the nucleon number. That's just the total number of nucleons in the nucleus. So for instance, plutonium-239 down here, we have 239 nucleons. That's protons plus neutrons. You'll write 239 up here. As a subscript on the left, we have the proton number, or the atomic number as you may recall it from chemistry. 6 for carbon, 92 for uranium. We just write that down here as a subscript. And this notation gives us a snapshot of everything we need to know about the isotope that we're talking about. So you'll see this again. Next thing we're going to move on to is what is radioactive decay and why it occurs. So radioactive decay is a naturally occurring, spontaneous, and random process that allows an unstable atom or an unstable nucleus, again such as plutonium-239, to decay into a more stable form, and eventually it will decay into something that is stable forever. A lot of the heavier elements decay into lead, and you'll see that in your chart of the nuclides if you go into the nuclear engineering track. So what we have here shown is plutonium-239, and that is the kind of the reactant side if you want to think of it in a chemistry perspective. So we've got our reactant over here, and that yields some products. So the plutonium-239 nuclide decays, and it emits an alpha particle here, shown by 2 protons and 2 neutrons. You'll also hear that called a helion or a helium ion. And what results after that decay is we're left with a uranium-235 nucleus. So we exchange a little bit of the mass in this system for some energy, and you can see here we get a reaction energy of 5.24 million electron volts, and that is conserved as kinetic energy both of the helium nucleus and the uranium nucleus. And so you'll actually be given some scenarios like this, and you'll calculate these Q values like this 5.24 MeV in the next lesson. So look forward to that. The next thing we're going to talk about is how we quantify radioactive decay. The first thing we need to know in quantifying radioactive decay is the initial population shown here as N0 on the vertical axis of this plot. On the horizontal axis, we show T to give us a function of time, and the curve on the plot shows us the population as a function of time. We can actually calculate the population at some time t using this equation shown here, where the population n is equal to the initial population times the exponential of negative lambda t, where lambda is your decay constant. That decay constant is going to be tabulated in a reference, or it's going to be given to you. It is a property specific to each radioactive nuclide. So let's take a look at our plot here again. You'll see I have 2 values, one on the x and one on the y axis noted for you. On the y axis, I have 1/2 of the initial population. So at some time after the initial population starts to decay, it's going to reach half of the initial population value. The amount of time that it takes for that to occur is noted here as T sub 1/2, and it's referred to as the half-life. Again, the half-life is specific to each radionuclide, and it is a function of the decay constant as you see here. We can calculate that half-life as the half-life is equal to the natural log of 2 divided by the decay constant lambda. Another interesting thing we might need to know about a radioactive substance, particularly if we have a decent amount of it, is how much activity or how much radiation is coming out of that substance at any one time. We can calculate that, and I do want to point out here we have 2 A's on the board. We have the mass or the nucleon number, and we have our A over here for activity. I encourage you to make sure your notation is correct and don't get those confused. So the activity is equal to the decay constant times the population at whatever time you're interested in calculating that. Now, if we make the substitution and simply multiply the decay constant times this entire first equation, we get the final equation you see on the board here, which is the activity at some time t is equal to the initial activity times the exponential of negative lambda t, again where lambda is your decay constant and t is your time. Stick with me, we'll be back in just a second. We'll talk about radiation dose and ALARA. Okay, now that we've talked about radioactive decay, let's talk about radiation dose. Radiation dose is simply the amount of energy deposited in your body per unit mass when you're exposed to ionizing radiation. In order to prevent absorbing dose from ionizing radiation, we use a principle called ALARA, as low as reasonably achievable. In order to achieve ALARA, we use 3 types of tools to accomplish that: time, distance, and shielding. When we talk about time, we simply want to minimize the amount of time we're exposed to any ionizing radiation. That's accomplished through prior planning and preparations with rehearsals. Distance, we want to increase the distance between the radioactive source and ourselves, such as I've done here. I've got my 4 types of radiation on the other end of the board. I've positioned myself as far away as I can get. And the final tool is shielding. That's what we're going to talk about in some depth today. So as you can see, I have the alpha, beta, gamma, and neutron radiations down here at the end of the board. The alpha particle is a relatively large mass, relatively high charge particle. It has a charge of +2e and a mass of 4. It is very easily attenuated and can be stopped by something as simple as a thin sheet of paper. However, the beta particle, which is a positively or negatively charged electron, is more highly penetrating and will pass through the paper. But a thin sheet of low Z material, such as aluminum, will stop a beta particle fairly efficiently. When we talk about a gamma ray, that's simply a high energy photon. It's very highly penetrating as well. It's going to pass through the paper, through the thin low Z material, but a thick piece of metal or a high Z material, such as lead, will stop a photon. Now the neutron is also very highly penetrating, and it's going to penetrate through all 3 of the first shields, but a very highly hydrogenous material such as concrete will stop the neutron, and that's why concrete's widely used in radioactive facilities such as nuclear power plants. You can see now that I've come back down to the end of the board behind all 4 shields that I'm absorbing no dose from any of the 4 ionizing radiations that we've talked about, and I'm achieving ALARA. If you have any more questions about radiation dose or what radiation exposure does to your body, please consult your instructor.